x-axis. So we can see here that there's a certain difference that comes in. In the first graph for embarked is equal to S, we see that the female gender is more likely to survive because of this, right? And if we look at embarked is equal to Q, we can also see that the female gender was more likely to survive. However, when it came to embarked C, the male customers or the male people are more likely to survive. So that only tells us that maybe embarked and gender are very good features to be used when we're predicting whether someone survived the Titanic or not. At this point, I'm just converting a few things, a few features that I think should be categorical, but it's really up to you. I'm converting them from numeric to category. So I've converted the passenger ID, I've converted the survived feature and the P class as well, because I think this should be categorical, or I want them to be categorical. I also do a bit more plotting just to understand my data set as well. I wanted to know if age would help me know whether someone was more likely to survive or not. So I used a box plot, and I didn't get much information from this plot because really the age, people who survived and people who didn't had similar kind of age. Like the median age was similar. We had a few outliers in those who didn't survive. So maybe we know that people who are young and people who are very, very old were more likely to die. But this could give us some kind of information. I did the same for the fare to just kind of understand if people who spent more money on their fare were more likely to survive. So you can do this for any of your fields just to understand what your data is like and to know what features you should play around with when you're building your model eventually. This is still exploring, which I think Joreen already went through as well. I did this also to help me know if I had certain correlations in our features. So you find that sometimes when you're dealing with so many features, some of these features or the X variables will be highly correlated to each other. So typically you don't want X variables, so many X variables that are correlated to each other, but you want X variables that are correlated to your Y, right? So imagine we have X1, X2, and X3, and X1 and X2 are very highly correlated to each other. You're probably better off using one of the X's. Eventually when you're building the model, it might help you with your accuracy as well. You also really, in terms of correlation, you want to check whether all your X's are highly correlated to your Y, because you want to include those that are very highly correlated to your Y in your models. Like when you're doing feature generation for your modeling, you want to include X variables that are highly correlated to your Y variable. So coming into the fun part, which is the model building, the ensemble models, what I did was, one, I got rid of some of the features that might not be necessary when we're building the model, like the name. At this point, I created a new column and a new feature called relatives that combined the SIB SP and the P arc, because I think both of these columns speak to someone's relatives. So I just combined them. So you can, most times you find that you'll also need to transform your variables. So you might find combining X1 and X2 together might give you a better feature to use when you're building your model. Or you might find that getting the log of a particular feature might give you a better accuracy when you're building your model. So for me, at this point, I just combined those two features, and that's why I'm removing them at this point. I remove ticket and I remove passenger ID because these two features are unique to a passenger, and you don't want to include them in your model building because then you overfit your model. So you'll find you build a perfect model because you've added IDs, and it will not perform well on your test data set, which won't be good. So I removed those two as well, and that leaves us with these features. I also noticed that I have a few features that are categorical, like the sex and the embarked features, right? So what I did was I converted these features into numerics at this point, so using one-hot encoding. So what happens is the female creates features different features. So if you have a feature called sex that has male and female, and you want to encode it, then a new feature is created called female, and a new feature is created called male, where if someone is male, it puts 1, and if they're not male, it puts 0, and then the same applies for the female feature. So it does this here for the embarked as well. So what this would mean is that this passenger embarked at C, and he didn't embark obviously at Q or at S. So you expect to have zeros for the other embarked features that were created. Another thing I did was, really at this point I'm just still trying to visualize and see if there's anything interesting that we can come up with, but we've already gone through this. So what happens next is you split your data set. So for the model I built, I split using a 90-10 training split, where 90% of the data was used to create the model, and then 10% of the remaining data was used to validate it. You always want to do this just to check your algorithm. Most times guys use an 80-20 split, and then also sometimes you find, we didn't have that case in this Titanic data set, but there are times, most times in the cases that you deal with when you're working, you find an imbalanced data set. An imbalanced data set will mean that, say in this Titanic example, imagine we have our Y variable as 1, the passenger survived, and 0, the passenger didn't survive. In most cases, you'll find that your say didn't survive is much more than the customers who actually survived, or the passengers who actually survived. So there are so many ways that you can deal with an imbalanced data set. We won't deal with that now, but then you can look into things like SMOT that kind of help you deal with imbalanced data sets, which are most real-world data sets. We split the data, like I said earlier on, with a test size of 10%. Here I'm just checking how many observations are in each of my data sets that I've just created, and then I build a bunch of models. You guys looked at logistic regression with Jorin. This is another type of modeling as well, linear discriminant analysis. There's KNN, which is also another classification model. Then there's the SVM, support vector machines. They're very powerful in most cases, but they take a very long time to run most of the time. Then decision trees. Then we look at random forests, which are an ensemble method. We looked at that. It's a bugging ensemble method. We look at adder boost classifier, which I mentioned earlier is a boosting ensemble method. And then we look at gradient boosting classifier, which is obviously a boosting classifier. And we see how well this performs for us. So we'll see from our results here that the SVM didn't perform so well from this snapshot or this graph that we are looking at right now. SVM and KNN didn't really perform well, but notice that the random forests, the adder boosts, and the gradient boosting did really well compared to the other models that are not ensemble models, which is very promising. So from this, actually I also encourage you guys to build multiple models just to kind of help you know which model to concentrate on. So from this, you'd probably look at the gradient boosting model and say, okay, this performed really well. Let's use that model to do our final predictions. Also, depending on the time it takes for the models to run, there's so many things that you have to put into consideration before you choose a model to use, like the time it takes for you to run, and the accuracy, obviously, and then the precision and the recall that Jorin mentioned earlier on, the error rate. You have to put all of those things into consideration. So you find that many times the models that perform really well take a long time to run, and they don't really work well in real life scenarios when you're at work doing something. So you find that you have to do a trade-off, or make a trade-off between time and accuracy. So I tried the model again for data that was normalized. Normalizing is really putting the numeric features that you have into the same scale, right? So we saw earlier on that the highest edge was 76, and then the lowest was about 0.17, and then we also saw that the highest was 0 and the lowest was 500 something. So imagine you have to compare those two features together. You're going to have the fare having a higher weight on top of edge because of the scale that fare occupies. So most of the time you find that you have to, and for some models you find that you have to normalize your data set, right? So I tried that. I said, okay, let me repeat the models, but with a normalized edge and a normalized fare. And we've seen this before. I split the data set again with a 90-10 split, and then I built the same models again. The logistic regression, KNN, SVM, decision trees, random forests, and again the Ensemble models perform much better than the other ones. We don't see much of a difference with the accuracies, but then we can see that for SVM performs much better, because SVM generally does better with normalized data, but the rest are kind of similar to what we saw earlier on. So after you've built that and you've decided on a model that you want to use, so here we can decide that we want to use gradient boosting because it performed better. We can now do actual predictions. So what I did here first was to look at the validation data set the 10% that we held out to validate our data or our model. We apply that model, we apply the gradient boosting model on the validation data set, and we get an accuracy of 83%, which is good. You have a confusion matrix here. I don't know if you guys have gone through confusion matrix, but it's good to go through at your own pace because it can get quite confusing, like its name. But we can see the precision, the recall, the F1 score, and the support. These are very good metrics to use when you're deciding on a model or when you're deciding on how well your model has performed. So you can see here that the overall accuracy of the gradient boosting was 83%, and this is of the validation data set that we held out earlier on. So then you can repeat this step. Now remember, we have a test data set that has no labels. So what you can do is just repeat this step, this particular step where we have model.predict for that particular data set, the test data set that has no labels to it. You won't be able to calculate the accuracy and all those things because there's nothing to predict, there's nothing to compare with, but those will be your final results. And if it's a cargo competition, that's what you usually submit. I added this just for fun. I think it's really cool. So someone can check and see what their likelihood of survival on the Titanic, if they were on the Titanic, how likely were they to survive? I did this for myself just to see how likely it would be that I would survive. So what happens is you choose a class, right? And these are all features that you've used to build your model. So I picked one. Then for when it comes to the sex or the gender, I picked female because I'm female. I picked my age, and then I assumed the number of relatives that I would probably have on the Titanic. I made an assumption that I paid $100 to get onto the Titanic, assuming that the currency is dollars. And then you also pick where did you embark from? And I picked 2. 2 is S. And so my likelihood of survival was 84%. I think this is really cool, and I'll share my code with you guys so that you can also try it with your different features and see if you are likely to survive the Titanic or not. So yeah, that's it for now for ensembles. Please do reach out to me if you have any questions. I will share this code and share the presentations as well as my email address for you to use. Thank you.